Okay. I think we're doing okay. That CPU's not happy. Projects. We will see if this goes live here. All right, we should be live. I'm gonna have to check. Got it going on my phone here. See when it comes up. It's loading, it's loading. There's a good 20 to 30 seconds of lag. So alright, we should be live. I'm gonna have to check. Got it going on my phone here. Let's try reloading it. I don't know if I'm actually getting video. Ah, there we go. Okay. It's loading, it's loading. There's a good 20 to 30 seconds of lag. Alright, I'm not going to share this out until I have... Why is this so much worse than it was? Like, I literally did a test stream like 10 minutes ago. Video. Turn off any outputs to change video settings. Yeah. 20 to 30 seconds of lag. Is it actually live though? No, I'm just dropping a crap ton of frames. Alright, I'm gonna stop streaming here. And see if... Oh, wait. See, it's like coming in and out. I'm gonna stop streaming. Okay, so that's a little better. 2700 seems to be a lot more stable. See, it's like coming in and out. I'm gonna stop streaming. Okay, so that's a little better. 2700. See, it's dropping again. A lot more stable. Alright, I'm doing like echoey stuff. Alright, I'm gonna see if I can keep OBS up. Kinda just check it every once in a while. Okay. Come on. Why am I not getting video? Oh my gosh. Alright, let me try. This is working like... which is not optimal. Yeah, it's literally the exact same message. Alright, so I downgraded the resolution to 1280 by 720. I think with you know, millions of extra people being home right now, my internet's taking a beating. See, it's dropping again. watching the stream to see if it's... Alright, well, it seems to be somewhat stable at least, so I'm just going to go ahead and share out a link. And then if any actual Stellar students are watching this, shoot me a private message if you're having stream issues on your end, because I'm more likely to see that than if I pull up the pull up like OBS or something while I'm doing CAD, because I'll probably forget. Alright, I'm going to copy the link and share this around to all of the various places really quickly before we get started here. I'm on my phone, so bear with me here. Facebook. I like how the thumbnail is just McMaster car. Pretty much for sure not gonna finish this project tonight, because it's pretty big, pretty complicated, but figured we'd get a good start on it, and maybe I'll finish it, you know, this weekend or something. Never live streamed before, so bear with me. Probably going to be really bad at it, probably going to have technical issues, and I don't have video anymore. Great. Yeah, that's not a thing that's happening. If any of you guys actually have any suggestions for how to make this like work better, let me know, because like I said, I've never done this before. I suppose I could oh right, I needed to put this on Chief Delphi too. Let me edit my post and just put a direct link to the stream. Yeah, like the bit rate's bouncing all over the place. I have it set lower than YouTube wants it to be. It kind of yells at me because the bit rate's super low. Yeah, I have all the programs that I use commonly. Do we not have video at all? Well, it doesn't want to play the video on my phone unless I refresh the page, so we'll I'll keep an eye on it and see if it's going to be an issue. Alright, so I have a little sketch I made here of the actual kind of the rough plan. It's going to be 3-stage. I just kind of picked that pretty much at random. That's kind of what a lot of teams are doing for climbing this year, but this is not really supposed to be for climbing necessarily. It's more just a generic design, more like what teams used in like 2018 or 2011 for picking and placing. It's not necessarily specifically designed for climbing, because when you're climbing, you just really need to spring load it up and then pull it back down with something, which this is actually going to be driven in both directions, just because it's more general purpose, so it's a better it's better practice to design a mechanism like that. It's easier to design something that's spring loaded and then pulled back down with a cable. So we're going to do this. So a couple things. This is a top view up here of just the sheet metal. There's going to be the final stage is going to be a 1x1 aluminum tubing. So everything's going to be sheet metal except for the final stage, which will just be a 1x1 box section. This is a side view, kind of a cross section, mostly just to help me remember where I'm planning to place all of the bearings and pulleys and stuff. We're going to be using a actual ball bearings to run this up and down. That's going to be the biggest challenge of this, is trying to fit those inside the tubes. But we're going to see if we can make that happen. Also, we're going to be using timing belts. One timing belt to drive the first stage, and then we're going to use some other timing belt runs to drive the subsequent stages in a cascading style rigging. We won't be using cables or cords or anything. We'll be using timing belts, but it'll work the same way as if you were using cables or something like that. So basically, we're going to stagger, so the drive belt run will be on one side, and then so that'll drive the first stage, and then the belt run driving the second stage will be on the opposite side, and then the final belt run that drives the third stage will be back on the original side. And that's basically just to leave room for the pulleys and stuff. There's not enough room for all of them on one side. All right, so let's get started here and start with some CAD. Like I said, I've never done a live stream before. All I've done is just record videos in OBS and upload them. I also typically do some planning ahead and some pre-CAD when I do those. So this might be kind of a mess, but we're going to go for it anyways. All right, so we're going to start with... I also don't know how my computer is going to handle live streaming and CAD at the same time. It's a bit of an older computer to begin with, so we will see. It could very well be kind of a slow process. It takes a while to load up the first part template here, but once we get one part created, it should go a little smoother from there. I'm working on Stellar Robotics' like server, I guess. It's just we just use Google Backup and Sync. Why did it do that? We just use Google Backup and Sync, and we basically just turn syncing on and off to make our files sync up between computers. We turn it off when we're actually working on something, so we don't have weird conflicts or file permissions errors. And then we turn the syncing back on when we're done. It's a bit of a laborious process. I'm thinking about trying to figure out a way to set up like an Autodesk Vault server or something better. So anyways, we're working on Stellar Robotics' file system. You know, we've got all of our previous robots here in this folder, including off-season stuff. I used to set up these folders and call them fall. This year I called it off-season because obviously it's not the fall right now. So made a folder earlier for our telescoping arm. So we have a bit of a part numbering system here. SR for Stellar Robotics, 20 for the season, F. We use F for off-season stuff usually because it stands for fall, but you know, we're not actually working on this in the fall, but it's fine. And then I'll just do TA for telescoping arm, and then this will be part number 1. And all of my students, you know, are familiar with this part numbering system. Basically, the whole purpose of the part numbering system is to keep the file names short and the same length, so they're readable. When you start spending a lot of time actually naming parts, you can actually spend quite a bit of time doing that. And so we don't like to spend a lot of time working on figuring out what kind of names we should call stuff. We'd rather spend our time actually CADing parts. All right, so a little bit of catch up here as I've been CADing while I've been talking. So this is the final stage, so this will be the third stage. Whenever we CAD stuff, we don't put any mounting holes in. I'm not sure of the length. I'm kind of targeting that like 3 foot size. We might shorten it down just so it's a little more applicable for like climbing mechanisms this year. But like I said, I'm not really trying to design a climbing mechanism. Maybe we'll put a hook on the end or something just to say we did, but that's not really the purpose here. I think we're going to use, all these dimensions are subject to change, but I think we're going to use, what are they? R18 or R188 bearings, which are 1/2 inch in diameter and 1/4 inch ID. We're going to use those. Those are the same bearings that are used on the competition robot parts elevator roller blocks. And I really like them. They're very small. They're cheap. They fit in tight spaces. So I think that's what we're going to use here. So basically, if we go back to our drawing here, we've got a 1-inch tube in here. And then we've got to have a bearing on the between the 1-inch tube and the next stage sheet metal. And basically, we're going to have to put some cutouts in the sheet metal for clearance, but we need enough of a gap in here that we can put a bolt in and not have it interfere with the side. So basically what we're going to do is we're going to have a bolt that runs across like this, and then there's going to be a bearing here that runs on one corner of the tube section in the middle, and then there's going to be another bearing over here, and then there'll be some spacers. And then basically we're going to do that on either side. Then we'll step like down, and we'll do bearings that go the other direction. These box sections, I'm not sure how clear it is on the screen, but these box sections here are made up of 2 formed sheet metal pieces that will then rivet together. Yeah, so I think what I'm going to do right now is I'm going to make this sheet metal section. It needs to have 1 inch. It needs to be 1 inch wide for, I'm basically modeling like this face here. It needs to be, where's my 1 inch wide, and I think I'm going to add 5/8 of an inch on either side for clearance. We might reduce that down later. Normally when you are CADing something, you have a few more design constraints like than this. We've got to kind of make up our own design constraints when we're doing practice CAD. I'm using 1/16 inch aluminum sheet metal. All right, so this needs to be 1 plus 5/8 plus another 5/8 minus the thickness of the material. So it should be 2.25 in that direction. It should be 2 3/16 in this direction. Yes. Okay, so then we're just going to put a 1 inch flange there. Actually, we're going to do that. All right, so then Autodesk Material Library. We'll set this to the correct material, which is this aluminum 5052 H38. That's exactly the alloy and heat treatment that we buy. Then I just give it the next number in the list. We're going to try to keep each half of the tube sections identical because they are rotationally symmetrical. So we can just basically take this part and rotate it 180 degrees, and it's this part on the other side. So I typically, when I'm doing CAD, don't do a lot of sub-assemblies because I find them obnoxious to navigate through. So we're going to kind of just plop this whole mechanism in one big assembly. If you don't choose to do it that way, that's fine. On your own CAD, that's just what I do. I think for people who are newer at CAD, it's probably better if you do make subassemblies, just because it's easier to keep things organized that way, and you don't have to worry so much about assemblies with a lot of constraints, where those constraints can start to interfere and cause issues. Changing my visual settings here to make this easier to work on. All right, so going to constrain that to there. I'm not really bothering. The purpose of this live stream is to kind of teach CAD and teach design. I'm not going to bother teaching the controls for Inventor. We've got CAD class resources from a year or two ago, a couple years ago, I guess, that go into all that stuff. So I'm using mostly keyboard shortcuts and stuff just to make this go faster and be a little more interesting to watch. All right, so what we should have right now is 2.25 in that direction, 2.25 in that direction. So we're just going to kind of rough out all of our sheet metal all the way up to the final stage. Also, I don't know why that grounded that first part. I shouldn't have done that, but it's fine. We'll unground it later. Okay, so we're going to place in our tube. I'm rotating things like that to keep known pieces of geometry at the top or the bottom. So that should be a 5/8 offset. That should also be a 5/8 offset. Now I think we're going to start with when you have a cascading mechanism like this, it's easiest to design it so that there is a part of each stage is sticking out of the previous stage. There are ways to design it so that everything's completely flush, but because I've never designed one of these before, A, I'm not 100% sure what those would be, and B, I don't want to take the time and effort to do it. It is possible my phone might die here. Should be fine for now. Okay, so I'm going to give this a save. I'm going to SR20F TA assembly 1. There will probably be only one assembly, but we might do some sub-assemblies for bearing blocks or something as we get farther along. All right, don't need that open at the moment. We're going to just go ahead and do a save as on this and call it 3. So this will be stage 1. Okay, so then what we're going to do is go in here, place this 1 inch with 2.25. It's been a few years since I've used SolidWorks, but a key difference between SolidWorks, at least when I used it, and Inventor, is that Inventor keeps those equations in those boxes, and SolidWorks kind of solves the equation and then gets rid of the equation, whereas Inventor, the equation stays there, which is kind of a nice feature in my opinion. I suppose it depends on how you use those equation features. All right, so going to do the same thing on this stage as we did on the previous one, constrain it all together in a way that makes some amount of sense. All right, and there to there, and that should be a 5/8 offset for all of these. That 5/8 number is kind of arbitrary, but mostly it's derived from it being, an 1/8 of an inch larger than the bearing that we're going to put in here. And now there can be slots for the bearings, and we may end up having to do that because we got to deal with like this flange and everything, and the gap between that and that is exactly 1/2 inch. However, I don't know exactly where I don't know exactly where the bearing is going to be, like left to right in here, because if it's right here on the corner, then it'll interfere with this flange, and we'll have to like notch the flange where the bearings are. But if we move it over a little bit, then the bearing won't clear completely. But then there's going to be a row of rivets running down to attach this part and this part together, and so we're going to have to pay close attention to that and make sure that we don't have bearings running over rivet heads and stupid stuff like that. So, all right, let's, I closed that part. I don't know why. Let's do one more save as on this. This was 3 inches, right? Not there. Oops, clicked the wrong surface. Oh, 3.5. Okay, so this is 3.5 in that direction and 3.5 in that direction. Everything is as it should be. All right. So then we'll do the same thing we did before. Take 2.25 out of here, put in 3.5. Oh, shoot, I forgot to pause. Yes. Hang on, I gotta wait for this to sync. Okay, pause syncing. All right. And then this flange, do the same thing. See, that's what happens when you don't pause syncing, is when you save it and it starts, as soon as you save the file, it starts syncing it to Google Drive, and then if you try to save it again a few seconds later, it won't let you edit the file. So you gotta wait for it to sync, then turn off syncing, then save it. All right. Oops. 1, 2, 3. Back where it was. Z. Now the reason I'm rotating this 3 times is just because I have a particular side of the sheet metal that I had intended to be the top, and another side that I intended to be the bottom, and I'm trying to maintain that. All right. So I went ahead and grounded this at origin. So I'm going to go ahead and unground the first part, so I can kind of move all this stuff out of the way. You should always have a grounded part in your assemblies, especially in Inventor, but it applies to SolidWorks and I'm sure Onshape too. I haven't used Onshape very much, but there we have it. Alright, so that's all locked into place, and we should be sitting at 4.75. So fairly bulky, but not an unreasonable size. If this were to be a primary mechanism on your robot, like an extendable arm for placing game pieces on some scoring element, then this would be a perfectly acceptable size for that. If this were a climber and you were to want 2 of these, one on either side of your robot, this might be a little bulky depending on what your packaging constraints are, but I think it's a good starting place for me, having not designed one of these before. Alright, so let's pull all this stuff out. Okay, so I think we're going to go... So when you're designing any kind of an elevator or something like that, you have, like, when it's extended, you've got this overlap. Not sure what to call it, but it's just like the final overlap of the stages. And basically, the smaller the final overlap you have, the more extension you get for a smaller overall package height, which is a very desirable feature. However, the more flimsy the mechanism is when it's extended. We're going to go ahead and be what I would consider fairly aggressive. I was going to do 4 inches, but now I'm kind of chickening out. I think maybe 5. That's still pretty far. Alright, so let's start doing some constraints here to kind of lock in this extension and kind of take a look at this. This is not super critical to figure out right now, because we can figure out later, but I want to start getting these in here so we can start putting components in this assembly. So I should click the other one first. And then there. Alright, so I think we're going to have them start at 1.5 inches because we're going to need a pulley, like a timing belt pulley, to stick completely out the top. Let's see here. Okay, and then the maximum that we could ever go. would be the length of the tube, which is like 36 inches right now. So if we want 6 inches of overlap, the maximum would be 30. So when we pull this out, it'll stop, and then we should be able to measure 6 inches of overlap. Yes. All right, so we're going to do the same thing on all the stages. We're going to click the lower stage first, then the upper stage, then fill out our minimums and maximums. So 30 max, 1.5 minimum. Make sure that that actually works. Good. And then this tube we might end up making a little longer because it's helpful to have a little extra sticking out the top on the final stage to actually mount your mechanism to. All right, so from here, so we're gonna set up the constraints the same way, but if we make this tube longer, we'll have to adjust these. So maximum of 30, minimum of 1.5. All right. Okay, so fully extended, we get, let's see, an overall height, that's probably the best way to do this, 126 inches. And with everything collapsed, I'm not going to bother rigging the like continuous versus cascading behavior of this. It's just too much of a pain in the butt. So it kind of acts like, if I pull on it, it acts like a cascading elevator at the moment where it pulls one stage up before the rest. But I'm not going to bother trying to rig it properly because that'll just make the CAD model more obnoxious. All right, so 40.5 when it's collapsed. 126 when it's extended. So that gives us 85.5 inches total stroke length, which is pretty good for something that's this short. I guess I should, yeah. So 40. So this is obviously way too tall to fit on a 2020 robot that fits under the trench. You know, you would need this whole package to be closer to like 22 inches or something fully collapsed. And that's including a hook. So this actual telescoping part would need to be quite a bit shorter, unless you mount this on an angle, like have it on your robot at an angle and then actuate it up with pneumatics, which a lot of teams have done. All right, so okay, so let's figure out where we're going. Stream seems to be okay. I see several of my students and several people who are not my students in the chat, so hello everybody. Let me know if we're dropping frames or doing stupid stuff. OBS is not happy, but it is functioning, so that's about all that can be said about everything right now. So one of the things you can do if you need to get more stroke length or a lower collapsed height is you can do some work to take this from 1.5 inches or whatever it is on your design and make this smaller, you know, bring it down to an inch, maybe get it down to ½ an inch. And as we get some of the more components in here, we'll kind of start playing around with those dimensions. So the next thing we need to do is get the bearing structure figured out. I'm not 100% sure if it makes more sense to put the rivet holes in now. Normally I say to everybody, do not put rivet holes in until you're absolutely done. But in this case, the rivet holes kind of will tell us where the rivets are going to be, which is a fairly major obstacle to the actual mechanical function of the mechanism. So it's probably going to be most helpful to put the rivet holes in. And actually, because I copied this part 3 times, I kind of wish I had put the holes in before I had copied it, but I guess that's what I get. So we're going to just go ahead and put these holes in real quick. We always, on Stellar, use 3/16 rivets. So that's what we're going to use here. The hole size for that is 0.196 inches. Use the hole feature, I always pattern the whole feature. I don't pattern the center points in the sketches. I pattern the whole feature. This will be like 71 holes. Yeah. We'll do one every half inch. When you actually build this, you would never put a hole every... you know what? Actually, because we're going to have like bearing shafts and stuff in here, I'm actually going to change that. I'm going to go to 36 holes an inch apart. What does 18 holes 2 inches apart look like? That looks better. We'll do that. Normally do half-inch hole patterns, but in this case, those holes are actually going to get in the way of stuff. So we'll leave it at every 2 inches right now, because that's all you actually need. I want construction geometry on. That's all you actually need for riveting this whole thing together. All right, so we're going to do a hole. We're going to do we're not going to send the hole through the back side just yet. We might go back and add the holes over there because they might be useful for mounting stuff later on down the road. But for now, we're just going to put it through just this flange. 2-inch spacing, 18 holes. All right, then we just got to do that 3 more times because I was an idiot and I didn't I didn't put the holes in before I copied the parts. So here we are. It shouldn't take that long though. Once you figure out a piece of geometry, it's pretty easy to go in and do it. Repeat it a couple of times if you need to. 2 inches, 18. Oh, did I type? Why did I do that? Okay. Construction geometry on. Notice I'm measuring to the edge of the very edge of the part. I'm not measuring to this tangent line. That's pretty important. Okay, so every 2 inches, 18 holes. Give it a save. All right, next one. This will be the last part. So what we'll do once we're done here, we're going to pull in some bearings and start trying to locate bearings for all of the stages. We'll start with the bottom one and just work our way towards the top. Or maybe we'll start at the top. I think we'll start at the top and work our way towards the bottom. Okay. 2 and 18. So you're watching in 60 FPS, huh? It's funny because OBS is only outputting in 30 FPS, so I'm kind of surprised it even gives you the option to watch in 60 FPS. It was at 60 FPS when I started, though, and I just stopped streaming and started streaming again, so maybe that's why. I'm not sure if that's what you're supposed to do or not, but it kept the stream going on my phone when I did that, so I figured if it didn't stop the stream, I was fine. But yeah, if you have any questions, you know, just type them in the chat or... Oh, shoot. Did I do that wrong? I did that wrong. Oh, right, because it has to be... Ugh, I can't believe I did that. This should be 1 inch. Now I got to think about whether I actually want to do that or not. All right, I'm going to go ahead and do it that way for now because I think we're going to put a bearing all the way up at the top because that gives us more support. So I think we're going to set the first hole 1 inch off the end. Normally I'd like to put a rivet right as close to the end as I can just for extra support. But in this case, I don't think we're going to be able to do that. So we'll go through and flip all of these to 1 inch. This is why it's nice that even though I didn't copy all these parts, I went and put all the dimensions and did all the geometry the exact same way, so that even though they weren't copied, you can't tell that they weren't copied. So I modeled every single one of these the exact same way. All right, give that an update. Okay, so then now we have the ability to rivet this together. And we'll go in and add, corner rounds and everything like when this is completely 100% finished. Let's flip over to our sketch here. Hard to tell, but basically these top bearings are going to mount to this stage. So there's going to be bearings on all four sides of this tube. Let's get an angle here. There's going to be bearings on all four sides of the tube. I think it'll be 2 bearings per side, because that'll provide some torsional support so that this can't twist and potentially pop out of the bearings. So there'll be 1, 2 bearings on this side, and then that'll be patterned all the way around. So 2 bearings on each of the 4 sides at the top. And then we're going to have the next thing is going to be the tricky part. I kind of wish I had thought of this before I modeled all of this. My plan was to have the bearings down at the bottom mounted to the upper stage. So like for the 3rd stage, this tube, I would have some brackets that would rivet to the sides of the tube that would support the bearings, and the bearings would roll on the inside of the previous stage. The problem with that is going to be twofold. First of all, the problem is this flange is at a different level than this over here. So that means that I have to have like 2 bearings mounted different distances, and I just don't want to deal with that because that's going to cause a whole cascade of a bunch of other problems and add complexity, because you basically have to put the bearings on different shafts, which is not particularly helpful. The other solution would be to potentially have the bearings roll in the middle, but that potentially gets in the way of the belt. I suppose we could do a kind of a hybrid solution where we have bearings that roll in the middle here, that roll right here on this outer piece, and same thing on the other side, and then we have a bearing here and a bearing here, and then there's room for the belt in the middle. So actually, I'm kind of wondering if it might be better to get the belts in here now and do that first, and then do the bearings after, because the belts take a lot more room and they kind of have to be in a specific spot, whereas the bearings, we can kind of just stick them wherever they fit. So let's do that, actually. Also, one note, I'm not going to do this. This is the drive, so this would be like the motor that drives this pulley. This is going to be moved down because there's only 90 degrees of wrap on this pulley, which is not enough to drive a high torque mechanism like this. But we'll cross that bridge. This belt path is going to be a pain in the butt to design. Probably not going to get to that tonight. I'm probably going to just place this pulley and this pulley and have just a dummy belt in there for now, and then come back and add the gearbox and stuff later. All right, so let's see. Let's start at the top. Basically, we need on one side, I'm going to say this side, we're going to need a pulley that's like, we're going to have to cut like a hole in here, and then we're going to need to have a pulley in here with a shaft that goes across where the pulley can kind of bridge the gap between here and here. The problem with that is from here to here is 1.188 inches, and that means that the middle should be right in the center. Is that right? Yeah, so the middle of where the pulley would be is right in the center of this piece of sheet metal, which means if we want to put a shaft going all the way across, we've got to cut like a slot in this, which takes away basically all of the strength. So I don't know. Don't really want to do that. So what I would rather do is shift the pulley to one side or the other, and then add spacer blocks or something. Because basically, if you look at this drawing, you can't really, it doesn't really do a very good job explaining it. But the belt is basically attached to this stage down at the bottom with a clamp, or I mean, you could even drill a hole in the belt and rivet it in place. I'm not sure the best way to do that. Probably with a clamp. That's probably how we're going to do it. Maybe a 3D printed one with some teeth in it. But basically, the clamp would go on the inside of the belt and bolt to this upper stage, and then the same thing would be done on the 2 stages previous to bolt to this stage, and that's basically how you rig a cascading elevator. So as this stage, the intermediate stage, goes up, this clamped spot here to the lower stage basically moves down relative to the intermediate stage, which causes the belt to roll, which causes the upper stage to move up in relation to the intermediate stage. That's kind of a difficult. It's kind of a difficult motion to describe. So if you don't understand what I'm talking about, I'm not sure I'm going to be able to do a better job explaining it here. It makes a little more sense if you see an animation of it, and it makes a 100% complete sense if you actually have like a physical device in your hand to move around. It's a fairly intuitive motion. It's just not necessarily intuitive unless you have a physical one in your hands. All right, so Stellar Robotics did a bunch of 3D printed pulleys this year on our robot. These pulleys aren't going to be transmitting much torque through their shaft. They're mostly just going to be transmitting force through their teeth, so 3D printed is plenty strong enough. Excuse me. So we're going to cheat a little bit, and we're going to just grab one of the Stellar Robotics CAD models. I'm going to grab this contracted one because that's a little easier. So we're just going to copy that. We're going to take it over to our telescoping arm folder, paste it down, give it a number. Oops. All right, then open it. All right, so this is 18 teeth. Basically, this is designed to be 3D printed with no support material, which is why the flanges have these like 45-degree angles to avoid creating an overhang. This is for a 15mm wide belt. We're going to do probably a 9mm wide belt. So we're going to make this a little smaller. But before we do that, this here, this diameter here, is basically where the top of the belt comes to. So this is 1.186 inches. And what's this gap from across 2 stages? 1.1. Oh, wow. It's like exactly the same size. All right, we got kind of lucky there. That being said, that still puts the shaft right in the middle of this, which we don't want to do. Let's see. Couple of things we could do here. We're going to modify the bore of this and just put idler bearings in here. And we're going to just use the same bearings for the this shaft as we did for the as we are for the rollers here. So let's do that right now. I'm going to suppress this. It's probably going to break a bunch of stuff. No? All right, cool. All right, so let's create a sketch. Let's project that and then slice the part so we can see what's going on here. All right, so what we're going to do is we're going to create, actually I want to do this on the other side as well. Construction geometry, actually no, I don't want that to be construction geometry. Okay, so we're going to connect the two with the center line. We're going to do a revolve cut because we're going to do a fairly complicated shape in order to allow this to be 3D printed still. All right, so we're going to make these two collinear. We're going to make, come on, clicking stuff underneath here. All right, that's going to be 45 degrees. Come on. That's going to be 45 degrees. All right, so this needs to be 0.196, which is the thickness of the bearing. Oh, where'd it go? Let's not do that. Let's create a few dimensions here. All right, 0.5, and then 3D print. Our 3D printers like to shrink by 20 thou on inside holes, so we typically add 20 thousandths to stuff. All right, so this side over here needs to be the same size as that. And this can be basically anything, but it just needs to be bigger than 1/4 of an inch. So we'll do like 0.25 plus 0.05 or something. Give it a little bit of a clearance hole. This will shrink up by 20 thousandths. So, all right, and then the reason for these 45 degree like chamfers here is we want, really what we want is we want a square, like we want a counter bore basically for the bearing to sit in, and then we want a shoulder on the inside of the pulley for the bearing to stop against. But we can't 3D print a square corner without support material, which we could do support material, but when you're using a fairly cheap printer like we are, support material kind of creates a nasty surface, and it's a pain in the butt to clean off, so it's labor intensive. So we always try to design our parts so that they don't need support material, and little tricks like putting a 45 degree angle on the top of a an overhang, I guess, is a good way to do that. So a bearing will go in here, and then a bearing will go on the other side, and then a 1/4 inch bolt will go through the middle, and then the 1/4 inch bolt will be the shaft that this just spins on. And then the drive pulleys will need to have this hex bore. We'll turn the hex bore back on for those, but we'll do a save as on this a little later when we're ready for that, and delete out what we did and turn the hex bore back on. Okay, so, oh yeah, we needed to change the width of this as well. So it's going to be, so this is the 15 millimeter wide belt plus a millimeter on either side of clearance. We're going to do a 9 millimeter wide belt, but we're going to add a millimeter on either side for clearance. I actually don't think we need a millimeter on either side, though. I think we're going to do a 1/2 millimeter. So it'll be 9 plus 1/2 millimeter on one side and a 1/2 millimeter on the other. So that'll give us 10 millimeters plus the 4 millimeter chamfered like flange thing on either side from like here to the outside face is 4 millimeters. So this whole thing should be 18 millimeters wide, which it is. 0.709. So how much room? Okay, so from here to here is 0.125. So that means if we wanted to keep a pulley centered, we could put like a little square hole in here and then have, how would we do that? I'm trying to figure out a way to have the pulley still stay right centered on this piece so we don't need to have like spacer blocks on either side. But I'm not seeing a good way to do that. Alright, I'm going to pull up a link here on my phone. sent it to myself earlier. Should be like way up at the top. Bear with me here. Alright, so pulley diameter chart, in case I needed to change the size of these pulleys. It only goes down to 16 teeth, but we shouldn't need, because you're not really, you never really make HTD pulleys that are less than 16 teeth. The belts don't really, they're not really supposed to bend that tightly. That being said, would be kind of nice if we could. Alright, so to go down 16 teeth makes the diameter of the pulley, this is an 18 tooth pulley, by the way. It goes down minus 24.32, so 3.18 millimeters in diameter. It goes down that much, which is like 1/8 of an inch. Yeah, almost exactly 1/8 of an inch. So the pulley diameter only goes down 1/8 of an inch, which only moves the center of the shaft from here, like right smack in the middle of this piece of sheet metal, over 1/16 of an inch, which doesn't really, excuse me, it doesn't really get us anything. Give me 1 second here. I need to respond to this. Okay, so I think we're going to leave it at 18 teeth. We are going to make these flanges a bit smaller to make the whole thing a little bit smaller, because we don't actually need the flanges to come up to be flush with the top of the belt. But we do want this whole thing to be smaller, so, or like narrower, I mean. So we can shave off some space in a couple of places. All right. Let's do this. This is kind of a mess, the way that I did this. This is 3 millimeters, and then this needs to be, I gotta change the way I did this, and then -1, like that. Yeah, and that changes both sides. And then I need to make the whole thing, and these, instead of 4 millimeters, need to be 3 millimeters. So that makes the whole thing a decent amount smaller, which saves us quite a bit of space. All right, I got my phone plugged in. I'm just keeping my phone up here so I can see the stream. Actually, I probably better close it. It seems like whenever I minimize it on my phone, it stops playing video and won't come back. But it is still live. How are we doing in OBS? We're doing okay. All right, so that pulley is basically done then. So now the width has gone down even more. So we're at 16 millimeters, 0.63 inches, which is nice and compact. So we can put a slot in this. Oh yeah, and I realized we don't actually need the slot to be on this side, because we did say we were gonna put it here. Is that right? Yeah, because we're gonna put a bearing in the middle on this side, and then on the corners here and here, down at the bottom, I mean. And so that means we can put a belt pulley in the middle here. Do we have enough width for that? We should. It's going to be really close, but some of this stuff we're going to have to just start going, and I'll figure it out as we go along here. Okay, so we've got our pulley. All right, so what we can do here, so we need to somehow have a a piece that suspends a shaft right in the middle of this part. So let me refer back to my sketch here. Yeah. All right, so let's take this, and this is why I had a specific side that was the top. This side is the top. And it's actually this bottom face. So what we need is, this is, well, we'll just do like 1.25 in this dimension and 0.7 in that direction. Project these two sides, put a line across the top, connect that there, and make that line vertical. Oops. I guess I did turn it, so it's that way. Can we make this point? Oops. Ooh, that's really close. How far is that? 1/8 of an inch. I think it's fine. Okay, so now, so that gives us clearance for the pulley. Actually, we'll just go ahead and cut that hole. All right, so there's a slot for a pulley. And this is the part where we might want to make the two halves different because we only need this hole on one side, and we're just losing strength by putting the hole on the other side. But for now, we're going to keep them symmetrical, and we'll call it a lightning hole on the other side. Not great practice, but it's fine for what we're doing. Okay, so now what we want to do is we don't want to have to take a bolt and go all the way across from one side to the other, because then, like I was saying earlier, we've got to cut basically a groove, like a slot in the sheet metal, which basically loses a lot of strength if we do that. So we would rather start the shaft in the middle somewhere, like kind of just like cut a small slot here, and on the other side have the shaft kind of drop into that cup and then stay there. So I can think of a couple of ways to do that. I think that they both are going to require that we design some 3D printed parts. I think do it with 3D printed parts. I'm trying to think here of a different way we could do it. I'm trying to avoid like machined parts, which we could normally use in this case. I'm trying to avoid machined parts because Stellar doesn't have a lot of like mill-based machining resources, and so that's why I'm designing this with the kind of collection of fabrication resources that we have. We have a sponsor that does sheet metal for us, and then we have a little bit of machining resources, but not extensive enough where I'd want to rely on it to make complicated parts for something like this. Okay, so I think what we're going to do is we're going to use a dowel pin, and then we're going to capture the dowel pin in a slot and then hold it in place with a 3D printed part on either side. I'll do a little bit better job explaining what I mean as we go. So this is what, 0.7? Yeah. And this whole thing is 2.25. Puts it from here to here. All right, we'll look for like a 1.5 inch dowel pin. Dowel. Plane. We need 1/4 inch. And then I need 1.5 inch long. What's like the cheapest one? Oh, these are like oversized though, aren't they? Black oxide. wondering if maybe dowel pin might be overkill. Maybe just a piece of steel rod would be better, because then it can then you can undersize it. Because otherwise, what you're going to have to do to get this dowel pin through the bearing is you might have to sand it, which kind of defeats the whole purpose, because dowel pins are really precise. I'm not 100% sure how this diameter tolerance compares to that of the bearing bore, because the bearing bore is slightly oversized as well, and it's going to be on the same order of like a few tenths, a few 10,000ths, that is. So this might be okay, but I'm not sure. We'll go ahead and use it for now. I think I already have a model of a dowel pin with the chamfers in it. I don't want to bother downloading that CAD model and then importing it. If I already have one, I can just modify. That would be under fasteners. We have a standard parts library. Yeah, I do. Okay, so I'm going to open this. This is one that's just shorter. Just do a save as 1.500, and then I want to put the McMaster part number in just so it's correct. All right, save. And then I even put in the colors and everything so it looks nice, because they cold head these, as far as I know. So they basically have a machine that cold forms them out of wire to make these ends, so they're really rough and not super precise in the ends. And then they put them in a centerless grinding machine, basically. It's a special machine that works in bulk and just grinds the cylinder, and it doesn't grind the ends. There are higher dollar ones, as far as I know, that you can get where the dowel pins have ground ends as well. But typically, the things that you use a dowel pin for, the ends don't matter, like what we're doing here. All we care is that the bearing slides nicely on the cylindrical part of it. Okay, so this is going to be 0.2. We'll oversize a little bit by like 5 thou. Then we'll do 1.5, and then we'll oversize it. Actually, we'll oversize it like, I don't know, 20 thousandths. That should be good. Okay. All right, so cut there. All right, so now, what's the smallest we can do this? All right, so basically the dowel pin will lay sideways, centered in this slot, and then we'll have something on the front that holds it and something on the back that holds it. And then we'll put a screw through the top and the bottom, kind of like a little pipe clamp or something, and then it'll be 3D printed. But we've got to make sure that however we fasten it, it's not going to like get in the way of stuff. Stellar's had a decent amount of luck tapping 3D printed parts. Not in high load circumstances. However, in low load circumstances, like what we're dealing with here, it should be okay. So we'll just have a screw on one side and a tapped hole in the other. And that should be sufficient. So, all right. Yeah, it doesn't matter. I don't need dimensions. Okay. So what we're going to do is a 0.255. Actually, I'm not going to oversize it like that. I got to account for shrinkage here. So, oops. All right, so make those collinear, and then so this offset here represents half the material thickness, because one is going to be on one side of the material, one is going to be on the other side of the material, and then the dowel pin is going to be constrained in the middle. So we'll make this so 1/4 inch And then we're going to need at least a 3/8 of an inch on the top and on the bottom for like support for the screw. So that's 3/8 plus 3/8, which is 3/4, plus another quarter, which is basically 1 inch. We'll just do an equals constraint, so that's symmetrical. And then this is the dimension that we got to be careful of, because we don't want it to stick up too far. Do we think we can get away with that? I think we can get away with that. All right, so we'll do this, we'll do that. We're going to want it at least that thick. And then 2 holes, 3/8 minus, should be just 3/4, like that. Oops. Okay, so then we're going to put just a tapped hole, number 10, 32. Oof, that's really close. Yeah, I don't like that. Wait, that should have been 5/8 of an inch, not 3/4. Like that. There we go. So now it's the same distance from the top as it is from either side. Okay, that looks more like what I was expecting. Inventor doesn't have PLA, so I usually just set things to ABS. This would get printed probably with this side flat because, well, it could get printed this way. Actually, this way. That's probably the better way to print it, actually, is that way. So it's okay to radius these corners because that won't create places where it's not contacting the build plate. We'll do a much smaller fillet than that. Okay, so then I never color anything until the part is actually complete. So in this case, this part is complete. We're not going to make any changes to this part from here on outwards unless we change the design. So I'm going to go ahead and color it the right color. Plus, we 3D print everything blue anyways. That's just the color of filament that we buy. Okay. It's just Twitter notifications on my phone. All right, now we're going to do a save as. We'll give it the next number. And instead of the tapped hole, we're just going to do a clearance hole, which will be 0.196 plus 0.02 for shrinkage. So those are quite a bit bigger. This part is on the lower boundary of what I would consider printable, especially for a mechanical component, just because there's not a lot of infill in this part. It's mostly perimeter, which can cause some weird gaps in the part where you don't want it. That being said, there's enough bulk kind of through the body of it that I think it's probably fine, and I would be perfectly comfortable having this part printed like for an actual competition robot during the season. Okay, so those were 5/8. I want to make sure, oh, stop it, we've got enough width here. Come on. Alright, so we got to be a little careful where exactly we put this, because there still has to be a bearing that rolls up and down on this part. Alright, let's add some holes. And I think what we'll do, I could probably just create a shared sketch for all this geometry, but at this point I can't really be bothered. So we'll have that 3D printed part basically flush with this edge, and then we'll shorten this slot up by however much we need to make, or no, I guess we can't because the dowel pin is only so long. We could get a shorter dowel pin too, actually. I wonder, So this is 1111 per 25. So what happens if we go down to a 1 3/8 or even a 1 1/4? So yeah, I mean the stronger alloys, they're just not that expensive to begin with. Okay, so we might go down to a 1 1/4 actually, just so we can shorten the slot up. And it's not really a problem if the 3D printed part is wider than where the 3D printed block is. That's not an issue at all. Okay, so then this is not a 3D printed part, so we don't need that 20 thousandths to account for shrinkage, so 0.196 is fine. We tend to run a little tighter. We try to standardize on the 0.196 holes just because they provide commonality between number 10 fasteners and 3/16 rivets. The 196 is a little bit on the looser side for the rivets and a little bit on the closer side for the 1032 screws, but having the commonality between the screw hole sizes is really nice, so it's worth it. We're going to go and create a sub-assembly of this actually with the bearings in it, because we're going to place like half a dozen of them, and I don't want to deal with having to put bearings in each one every time we do it in the main assembly. Let's change the visual style so we can actually see where all the edges are. So under standard parts, under bearings and bushings, so that's an R4. The CRP bearing block somewhere. Oh, there it is. Yes. Okay. And actually, why is this? This is not supposed to be stainless. Should be steel. And then the appearance should be semi-polished. Ugh. Can I edit properties? Clear all overrides as part. Oh, you gotta be kidding me. Did that not work? Guess that didn't work. Okay. I'm not sure what's going on. Alright, close enough. Anyways, alright, so insert the bearing there, flush with the outside, and then same thing on the other side. And then if we look at the way this works internally, there's a little bit of gap here just because of the shrinkage, because we're counting for the shrinkage of the 3D printed part, but not an issue. We did these for some pulleys on our climber for this year's robot. So we'll call this assembly just assembly 2. Basically all it is just the pulley with the bearings in it, but that'll make placing them easier down the road. Okay, don't need that anymore. Okay, so let's place we want these on the outside. So we'll use the insert tool to constrain there. And there. And then there and there. That's technically over constrained, but Inventor doesn't scream at me unless they conflict, which we'll just make sure they don't. And then this is bigger than what looks like it should be, just because we're accounting for shrinkage on that part. Alright, so now we're going to do the 6, and that's on the back side. We'll do the same thing with the insert constraint. I can't see that hole. There we go. And it's going to be a little tricky. I'm going to have to get it back from the other side, I think. Yeah. All right, so that to that hole, and then from the other side, the threaded hole to the aluminum. All right, so now we've got this there to there. Should be a center distance of 0 because they have a common center, even though it doesn't look like this is a circle, just because, like I said, we modeled it oversized for different shrinkages and tolerances between the aluminum and the 3D printed part. It is actually correct. All right, so how much do these stick out? Oh, it's just like a tiny little amount. Oh, okay. So it's not really worth shortening the dowel pin just because the difference between this being a here and this being in here is not going to be the difference between a bearing being able to roll on this surface and not. And actually, a bearing never actually needs to roll beside these, which I just realized. I mean, it's past my bedtime, so I'm going to give myself a pass on that one, but I just realized I didn't even need to worry about the bearings because the bearings, this never goes down any farther. That's the whole point of having the pulley up high like this. Okay, so all right, moving on from there, that just makes our life a little easier. So fasteners, the new dowel pin. We'll use just a center line constraint. And then how wide did we make this slot? We made it a little oversized, so I just want to make sure it's actually centered. We 20 thousandths oversize. So that from there to there, yeah, it should be like that. So that is an even gap. And then in real life, this dowel pin will be able to slide. Oops, we'll be able to slide back and forth a little bit, but it doesn't matter. All right, so let's get our pulley assembly in here. This guy. All right, and so this is 0.630, and this is 0.7. So 0.07, so 0.035 should be the gap. We'll just use the insert tool. Insert to that 0.035. So to do this properly, there should be a spacer in here. That's such a small gap that you might be able to just do it with like a washer rather than trying to 3D print or cut a spacer. Because it's Stellar Robotics and our motto on Stellar Robotics is sketchy at best, we probably just wouldn't put a spacer in there and we would just let the pulley rub against the aluminum every once in a while. If we were really worried about it, we might just put some like lubricant or something on it. Although, because this is a belt, that's not a good idea because lubricants can attack the rubber depending on what you use. So we probably just wouldn't worry about it. But there really should be a little spacer, a tiny little spacer in there that only contacts the inner race of the bearing. I'm not going to model it right now, but maybe we'll do it later when we're putting the finishing touches on this whole thing. Okay, so from the front surface here to the back surface there, it's about a 1/2 inch. It's a 1/2 inch plus the 1/16. I'm going to go ahead and see if I've got a model of a button head screw. I do not. I'm going to go ahead and get one. Actually, hang on. We did those CAD class videos. Oh my goodness, I don't remember which weeks those were. Oh right, they're not actually in here. They're in 2018 fall, I believe. CAD class gearbox. All right, I'm just going to copy and paste. Paste, okay, and then we just do a slightly different naming convention. So screw on the front, so that all the screws show up in the same area of the file because they're sorted alphabetically. So we put screw first, but that's only 3/8. Dang it! I'll leave it in there. We'll use it at some point, but that's the wrong screw. Gearbox. Yeah, this is the one that I wanted. The 1/2 inch long button head. Okay, paste that in there. Put screw on the front. And then BHCS on the back. How's the stream surviving? How's OBS doing? I'm like the Bob Ross of FRC. You know what? I'll take it. Thank you, sir. Okay. Oh, I didn't actually want to open that. I just wanted to place it. Standard parts, fasteners, and the 1/2 inch long one. And then we need 4 of those. I hate patterns. I hate patterns in assemblies. I don't know. Patterns and I don't seem to get along particularly well. This would be a good application of a pattern, just to do a place one screw and then do a rectangular pattern. But I've always had better luck just going and constraining each one individually. I find like if we're to make this part longer, we don't have to go in and edit the pattern. We can just rely on the constraints to move the bolts where they need to be. Okay, that is fairly neat, I think. I still don't particularly like the fact that we have to make these tiny little 3D printed parts, but you know what? I'm going to stop worrying about it, and I think we'll just call that good. It looks like it should be free of interferences with any of the other stuff that we're going to do, so we'll kind of leave it at that and move on. Actually, we're not going to move on. We're going to do the exact same thing for the next stage. We don't need to remodel any of these parts. We're going to use all the same parts. We just need to cut this like slot and these holes in this part here. So we get this guy open. So let's start with this. 1.25, 0.75. Okay, easy enough. Grab this part. We know this end is the top because they're all modeled and constrained the same way. Start like this. And okay. 1.25, 0.7. And cut. All right, so then we're going to do the same thing here. And then we did 1.5 and then 20 thousandths oversize, I believe. Yes? Yes. Okay. And honestly, I could put these in one cut feature, but I kind of just like drawing the rectangles. Makes it a little bit easier to do this over and over again, just separate ones. Kind of just personal preference. You do things differently, like if you've got to model something over and over and over again, like for a company or something, like at work, and you know it's not going to change, or not going to change that often, and you have to do a lot of similar parts, you're going to model certain things one way. But when you're working in something like FRC where you've got to model it once, you're going to have to change it a bunch of times. You don't have to do a ton of repetition. You're going to model things a little differently. So you just kind of have to build your own kind of CAD conventions for the type of work that you're doing. The important thing is just to make sure that you do it the same way every time. So if you're gonna approach something, you're gonna model the same part the same way every time, especially if you're gonna model similar parts in something like a single FRC robot. And then also if you're working in a group, like if your team has, multiple CAD people, you're gonna you're gonna want to make sure that all the CAD people are kind of on the same page in terms of everybody's conventions and how everybody does things, and preferably you find a way to standardize between all the people doing CAD so that everybody does the same things the same way, dimensions holes the same way, uses the same tolerances for like oversizing holes, uses the same size fillets, just simple stuff like that where you'll start to get weird interrelations between different designers doing things different ways. It's just good practice. Oops, I didn't want this top one. I want to draw that. Okay, so I kind of did this one backwards, but it's fine. Nope. Just fat fingering my keyboard here. All right, cut that one. Then we'll do the slot for the dowel pin, and then we will do the holes. And then I just went ahead and did this part before I constrained the stuff in the assembly, just because I was on a roll and was going to be able to just knock this one out real quick and then do all the assembly all at once. And the only reason I'm putting these angled lines is so that I can use the midpoint to constrain the center point rectangle for the whole pattern. I assume that was self-explanatory, but I didn't mention it as I was doing it. That's a very common thing that I do, a little trick I've come up with. I'm sure other people do it too, but it's just something I kind of discovered on my own in the wild. Highly recommend. 10 out of 10 would recommend. It's a good trick to use. Okay, so all right, so now we've got this like slot thing. Like I said, we don't need another pulley on the other side. If we were doing something crazy or we were worried about only driving this from like one side, we could do it symmetrically, but it's not really actually no, we couldn't, because the way we're designing this, we're going to have a pulley over here and having a pulley and a belt running down here and a pulley and a belt running down there. They would interfere, so I take that back. Okay, so let's see. We need our telescoping arm, the unthreaded one, 2 of those, and I'm just going to go ahead and plop those down as well. And actually I'm going to constrain these first. That way I don't have to like do that whole thing I had to do on the last one where I have to like look through the hole of the outer part to constrain the inner part. So I'll do the inner part first, then constrain the outer part. Because that'll make my life a lot easier. Alright, there and there. And see, once you've done it once and figured out how you're going to do it, it goes a whole lot faster the second time. Okay, oops. Assembly 2, insert, pick the outer, nope, come on. Whenever I click the wrong thing, I'm just hitting escape and then I'm hitting the C key really fast just to close that window and bring it back up. That's kind of the fastest way to reset the selection. You can deselect stuff, but I found it's just faster to just hit escape and hit the C key really quickly. I've always got my hand on the escape key, or near it anyways. I put my hand in a specific place on the keyboard that allows me to reach the keys I use most often. Right, we need the dowel pin. I can't remember how I did this last time. Just, yeah, like that. Oh, come on. center line, and then I just did, I think I constrained this. No, I definitely had the blocks in last time I did it. All right, okay, so that's done. So now we just need the little screws, and then I think we need to place one here as well. So we'll just do that the same way. And that outer one is actually going to be driven. So like we're going to put the idler, which is what these are. These are just idlers, but down at the bottom, because like we're going to have to do something similar to this down at the bottom of each of these stages, which we're probably not going to deal with until after we get the bearings in there, because down at the bottom is going to be a little crunched for space. We haven't really talked about it so far yet. However, assembly for something like this is a very tricky and a very important thing to consider. I put a little bit of thought into it before I started modeling, probably not as much as I should have. But as we kind of get into the clamps for the belts and some of the bearings and stuff that go in here, we're going to have to talk a little bit more about that and make sure that it's actually physically possible to assemble this thing. No telescoping mechanism is easy to assemble. There's some things you can do to make it easier on yourself. We're not going to, like I said, this is my first time modeling something like this, so I'm not really going to worry too much about whether it's really easy to assemble and maintain. Mostly I'm just going to get it to the point where it's possible to build and then call it good. And then if we feel like going into doing another revision at some point, you know, that would be a project for like a second iteration to improve how maintainable it is. Okay, so just keep on going, keep doing the same thing we've been doing. This is not really a Stellar Robotics project. This is more just you know, with the coronavirus, you know, a lot of people can't meet, can't work on robots, you know, and a lot of teams are working on trying to kind of do some training and improve skills and work on new projects and stuff, remotely or with, you know, small groups of people in meetings, while there's no competitions. So I figured, you know, I would just do this because I didn't really have anything going on this evening. We're obviously not going to finish this. I'll probably stream until, you know, 10 o'clock, and then probably call it quits for the night. But I might do another stream this weekend or something and finish this up. This is kind of how I did the CAD videos on Stellar Robotics' YouTube channel. I just came up with a project, did a little bit of planning ahead of time, and recorded a series of videos. But for this, I figured I'd do it live. Yes, to answer your question, we'd actually 3D print them separate, like so the outer parts would just be 3D printed with a bigger hole. The inner parts would be 3D printed with the hole that's about the tap drill size, and then we just run a tap through that. It's not great for high load stuff, but Stellar Robotics has done a considerable number of tapped 3D printed parts, and in low load applications, we've never had it fail. In high load applications, it definitely causes problems, but it does work for something like this. So yeah, that would be the plan. You would just run a hand tap through each one of those holes, and you'd screw it in from the outside. Yeah. Okay, so that's good. Just need the screws on that one, and then we'll be done with these little blocks, and we can move on to the actual bearings. Yeah. Okay. Get constrained as quick as possible. Okay, so that is done. So basically, just to kind of review, this pulley, there'll be another pulley and like a motor down at the bottom. And so you'll have this loop of belt, just like in the sketch. It'll go down, and then there'll be some sort of like a tensioner, idler, and it'll run around the belt, the motor pulley, which would be this circle here. And then basically, we would, down at the bottom, this stage here, you know, the belt runs down beside the stage, and we would use a little clamp or something to clamp the belt to this stage. So as this belt turns, it raises this stage up. And then as this stage goes up, we'll have a belt run over here, and this belt will bolt to the bottom of this stage. So there'll be another little idler just like this down at the bottom of this stage here. So basically we'll just do the exact same thing down at the bottom probably. I'm going to wait to actually do that until we get the bearings and stuff down here at the bottom to make sure there's no interferences and to make sure we don't have to design this little assembly differently at the bottom. But basically, as far as I am thinking at the moment, we'll just literally do this exact same thing down here at the bottom. So we'll have this loop of belt. Oh yeah, that was the other thing. There's not actually a way, I meant to address this earlier and I forgot. There's not actually a way to get the belt in here. Because it's a hole and the belt is a loop. So you can't feed one end of a loop through a hole. So actually I think probably what we'll end up doing is we've got to have some way to get the belt in here. So I think we'll probably just cut the top open. The only thing I don't like about that is it kind of reduces the strength of the part, but there's so much aluminum down here adding support that this little piece across the top's not really doing anything. So we'll probably cut this and open it up. The other option would be to cut it to the side, so you can like slide the belt in from the side, but I think the top is going to be easier. The big thing is just making sure that when we do this at the bottom, there's enough room to like stretch the belt and work it around this flange and get it in place, which there probably is. That would be my only concern, because the belt's, you know, the belt's not going to have any extra length. Like when the belt is on this idler, it's going to be tight, and so you can't like stretch the belt up to get it off. So I think you probably, to assemble this, you'd probably not have any of these blocks and stuff in place. You would get the belt in place first, then get the pulley, you'd get the dowel pins through the pulleys and stick them through the middle of the belt somewhere, kind of work them to the end and drop them in place, and then put the 3D printed blocks on, I think. I'm not sure. What we might need to do to make this a little more feasible is to extend this slot down so that you can kind of pull the dowel pin out this way and slide the whole thing that way to reduce tension on the belt just for assembly. So like make this cut like a 1/4 inch deeper. So actually, let's see what that looks like for a second. So if I do, oh, not that one, this one. So we want to cut the top out and we want to cut another 1/4 inch in the bottom. So I'm just going to make this a 1/2 inch longer, and that'll accomplish both things. And then it's going to scream at me. Right. Yeah, that broke stuff. So actually what I need to do now, okay, well that's broken and I'm going to have to fix that, but I'm not going to do that at the moment. You know what? Yeah, I'm going to do it. I should do it the right way. Do it right. Okay. Delete that. Delete that. And then what I'm going to do is project that and do this a little differently than I did it before. So this will be 1.75 divided by 2. And actually, if I wanted to do that, whoa, is that right? Yeah, so D47 is that dimension. So if I want to do it right, I can make this D47. And I'm getting the dimension by looking up here at the little title bar. It tells you what dimension. So if you type in dimension, even if it's in a different sketch, it'll still go and pull that dimension value. Oh, and I forgot to make this aligned. Oh, hey, Theron. Belts. Mostly this is because I said it right at the beginning of the stream. I don't know when you joined, but basically I'm not really necessarily designing a climber for the 2020 game. Mostly I'm just designing a telescoping arm. So I decided to go with belts just because I had never designed one that used belts. I felt like constant force springs were probably an easier thing to design than something with belts. So that's why I chose to go with a belt design, so it would be drivable in both directions and it would be more usable for like a pick and place game rather than only climbing. Yes, you are very late. Probably got like 15 minutes left before I decide to go to bed. All right, so D47 divided by 2. That's the dimension that we used before. I'll center that up. Okay, so that's that. So like this being an open notch does sacrifice some strength, but not as much as I was worried about, I guess. The other thing that I'm a little worried about is how close that is to the edge. That's not strictly speaking great for bending, but it's such a narrow thing that it might be okay. Normally, you got to be really careful how close you put holes and stuff to the edge of a bend, because when you bend sheet metal on a press brake, stuff like this just doesn't bend, and you get weird like warping of the holes. And this is a prime candidate for that. So what I might end up having to do is do what we were talking about doing earlier and actually shorten the dowel pin. Yeah, Max, I can. So this is what we've gotten done so far. Basically, we did the sheet metal and we designed these little pulley blocks, and we're pretty much done with the pulley blocks. I'm not going to go ahead and open up these holes for the rest of them. We'll do that next time, or maybe I'll do that off camera before I start the stream next time. You saw me do one, so I kind of want to start working on bearings now, so let's start doing that. So top or bottom, that's the question. So let's go here. So the plan is to have at the top, the bearings are going to be attached to the, I guess, lower stage and roll against the upper stage. So we'll have a shaft through here, and then the bearings will roll against this stage. And then here we'll have a shaft that goes through, and the bearings will roll against this stage. On the bottom, give me 1 second here. I'm trying to make sure that my assembly is still, oh yeah, okay. The video froze on my phone. I wanted to make sure I was still sending stuff. How are we doing here? I think as it got later in the evening, I think maybe people started getting off the internet in my neighborhood, and the internet got a little bit better. I did a speed test earlier before I was streaming, and I was only getting like 15, 20 megs, which is still enough to stream presumably, but it's I pay for 100 and I usually get like 120, so I just have Spectrum, so it's just normal cable internet, I guess. All right, so what we're gonna do here is on the top. The problem is we kind of don't have room to put a shaft. So from here to there is 0.194. So let's go, let me open up this bearing. I think it's just, yeah, because this is a 1/4 inch and this is a 1/2 inch. Yeah, that's what I said. Okay. So, yeah, so that's 1/8 of an inch between, so we have a bolt that goes through here. Basically, there's going to be 1/8 of an inch between the surface of the bolt and then the surface of the bearing. And so I'm kind of just doing some head math here, trying to figure out, like, can I squeeze a hole in, like, right here? I think the answer is no. And so what I think I'm going to have to do is move this down a little bit, which is not actually that big of a problem because we're going to have to move this around later anyways once we figure out, like, what belt center to center distance we need to use, because that's going to kind of define exactly where this needs to live to get the belt, the pulley center to center distance and the belt length exactly right. We can't move it much though because we really can't go below here, just because well, we could a little bit. We'll start running into issues where we're going to have shafts that go through here that have bearings on them, but that's not, we're not really anywhere close to that at the moment. So, okay, so from here to, let's just do this. This is going to be easier if I just do it this way. Let's just put the holes in there, and then we'll move them later. All right. Okay, so these are these construction circles represent the bearings. I want to do this kind of the same thing I was doing before. The center point, make that line vertical. I'm actually using the horizontal constraint because this is turned on its side right now. I'm going to use a work point at the intersection of these two circles. I'm going to do 1 inch there. You can play with this a little bit. You might even want, if you really wanted to like preload it so there's no slop in your mechanism, you might want to, you know, do like 0.995 or something. Not really going to worry about that right now. These are going to represent the actual holes. I'm going to use the actual hole feature, but I'm putting these construction circles in here to kind of visualize. Oh, the other thing I should do is put a 3/8 circle in. The 3/8 circle represents the actual bolt head because we're going to use a like a socket head cap screw. So long story short, this is way too close to this. We need like a lot more room. I don't really want to go any closer than that to the edge, which puts the bearing like flush with the top anyways. Just because this only leaves like 1/8 of an inch of aluminum between it and the edge, which when you're laser cutting stuff, you got to be kind of careful how close you get holes to the edge, because if you get a very thin piece of aluminum, like even this is a little bit worrying. It'll be okay, but if you get too close, the heat from the laser can just melt straight through a very thin web. This is, like I said, this will be okay, but if you get really close, like if you went half this distance, you'd probably just melt right through it. So you got to be kind of careful of that. Okay, so we'll do 0.255. That's a very close fitting clearance hole for a 1/4 inch. Very close fitting. Also, this hole's really close to this bend. It's not as much of a problem with a round hole as it is with a square slot. Like this, you probably get away with it. You will end up with a little bit of distortion though, and you'll have to chase it with a drill bit, like for sure, 100%. But you might have to do that anyways just to get rid of burrs because this hole is going to be so tight fitting on that screw. But that's important to make sure that you don't have any slop in your bearings, because then you'll have slop in your mechanism. Alright, so, and then there'll be like, come on, then there'll be spacers and stuff stacked up in here with the bearings too, to put everything in the right spot. So let's figure out how long of a screw we need. It's probably going to be some weird size, which is going to frustrate me. 2.5. Alright, that's not bad. I usually allow 1/4 of an inch for the nut. That works pretty well. It's very close. It's just barely enough, but it will work. And I think we actually have that size in here already. Yeah, we do, because we used that on our 2019 elevator. Okay, put these in here. Alright. And then there's just barely enough room where you can get a nut, and it starts to engage the nylock on this side if you use a nylon lock nut, which in this case you definitely should. What is going on here? Oh, right. Oh. Right, I can't center those holes. Oh, wait a minute. Did I do that? Did I make that mistake on everything? I think I made that mistake on everything. This probably isn't centered, is it? Because it's centered on this part, but it should be a 32nd of an inch this way because I didn't account for this piece of sheet metal over here. Alright, well that's not a big deal. It requires a little bit of work to the sketch, but so basically what it means is I can't do that at all. I have to do it. I have to do it like with a dimension. So this is the actual outside, but there's another 1/16 of an inch piece of metal on this side. So I need to shift everything a 32nd of an inch that way, and then I got a dimension to the top. Okay, and then I need to actually do that with like this too. I probably only need to do it with this sketch. Oh. Put a point there. I don't care, Adobe. Go away. Alright, and then add a 32nd of an inch. Alright, so now everything should be... I have to do that same stuff for this too, but it's relatively painless. Okay, so from here to here, 365, 365. Wait, why is it? Oh, right. It's 375 plus a, or with a 10,000 sticking out of it. Okay, so from here to here is 0.150, and from there to there is 0.150. So yeah, everything's centered now. Okay, so then yeah, this is the interference here that we've got to get rid of by moving these blocks down. Unfortunately, that's going to bring back that little web at the top, which we can take care of that another way. So how much like actual space do we need here? Now there's a nut on the other side, and the nut actually takes up more room than the screw head does, but we can kind of avoid that problem by putting the screw heads on the same side with the idler and the nuts on the opposite side. And so basically the screws would need to go in the other way on this stage, so the nuts are over here and the screws are over here. But on this stage, it's not as much of a problem as it is on this stage, because these bolts will be like way out here, so they won't interfere at all. It's only an issue on this tiny top stage. That being said, we'll probably still move this down just to keep the belt center to center distances all the same, because it's going to be obnoxious if they're all different. And it doesn't really get you anything to make one stage a little longer than the other one. If you're going to make them all short, or if you're going to make one of them short, you might as well just make them all short. All right, so that, oh, it's like right on there. So we've got to do a minimum, an absolute minimum of 3/16 of an inch downwards. We'll probably just do a whole 1/4 of an inch. So if I go here and I make that 1 inch instead of 3/4, I'm going to make that solid, like actual geometry. I'm going to just close that off. Then what I can do is go in and select this other profile. And now it's going to scream at me again. What did I do now? Oh. That's fine. Okay. Like I said, I'll carry over these changes to the other stages either next time or off camera. Okay, so that is relatively interference free. The only issue we've got with using bolts that are this small is we're going to end up with like screws or with bearings that are like right on these threads, which is not great, but we had the exact same issue on our 2019 elevator and we never had problems with it. So I'm not going to worry about it here either. Okay, so I'm just going to go ahead and drop some bearings in here, and we'll kind of take a quick look at it, and then we'll probably start wrapping up here. Call it a night. Got work in the morning, so should probably go to bed. Okay, so it doesn't matter. I hate these new directional axis constraints that Inventor added. I'm sure they're useful for something, but most of the time they just annoy me. Oh yeah, that was the other thing too. Yeah, because we're gonna do one in the middle here. Is that right? Because we're gonna have this problem. We're gonna have this problem on every stage where if we try to put a bearing right here at the corner, we've got to notch this flange. But that was kind of the point of putting this hole like not really close to the top, because we can just like cut part of this flange away and it's not going to take out any of the strength. So I think we're going to just do that, and we're going to have 4 bearings. I don't know that this upper stage really needs it, just because, I mean, it's a single tube, so having like 1 bearing in the middle on these 2 sides and then 2 bearings on the other sides is probably fine. Now, we absolutely have to have... Wait, how did I plan to do that? Oh. Okay, so these bearings are supposed to be above this pulley. All right, so we're gonna have to just get like really really creative with how we squeeze everything in there. So we might need to actually push this down a little bit farther to make some room, or we might have to just buck up and move these up a little bit. All right, I'm not gonna worry about it right now though. So there to there. There to there. Okay, so that's basically the generic bearing arrangement, and then there'll be little 3D printed spacers in all 3 of these empty spaces to kind of keep these located. And then basically we're going to do the same thing in the other direction. So we'll put holes like here and here, run bolts across like either slightly below or slightly above these, and have bearings that run on the other side. The big issue is we've got to make sure those bearings don't interfere with this belt pulley, which is going to be a bit tricky. I'm not sure that we're going to be able to get away without moving this down more. Moving this down more, yeah. The problem is that like we're gonna have like bolts going across here as well, and so if we move this down really any more than it is, we're gonna start interfering with those bolts. That being said, if we go this way first, and then we have the bolts that go across this way below these bolts, like if we put the holes like here, then that puts the holes that go across this way like down here. Okay, well that's going to be a bit tricky, but yeah, I think it'll fit. We're just going to have to kind of move stuff around as we work. And this is how design always works in FRC. You never just model it and get it right the first time. You're always going to have to go back, and you're always going to have to make tweaks to your design. So it's important to do your CAD in a way that allows you to make changes to your design as you go. All right, well, I'm going to go ahead and call that tonight. I'm going to say that's going to be a good amount of work done for one night. I will try to do another stream sometime soon. I will see you guys then. I'll post links and stuff on Chief Delphi and Facebook, and just like I did for this one, I'll probably just reuse the same thread and just post a reply with an update with a new link and a new time. So thanks for watching. Obviously, this video will be archived on the Stellar YouTube channel, so if you're watching this in the archive after the live stream, then thanks for watching. There will be more videos to come. All right, good night, guys.